So,
Okay.
okay. So can everybody see this nice Python, this notebook I have here?
Yes.
Okay. Good. So I'm going to go through a couple Python things that will be useful both for Ali, but also I think, Debbie, it'll help to see. Uh, this is just going to solve the equation that you just solved. At the end of the day, we're going to solve something which is very similar to the neutrino thing you just did, except I'm going to put different words on it. Instead of the probabilities, instead of the numbers being the neutrino mixings, I'm just going to have
Hmm.
the story about two people, Romeo and Juliet, and the numbers in the matrix are going to be A, B, C, and D here, which it's the same math, but just different words. Um,
Okay.
okay, so let's do this first. So first I want to explain this e to the I stuff, because I realize that no one has seen this in trig, right? What it means to take e to a complex number. Is that right?
Do a complex number. I've never done it with a complex number, but I imagine it works. Does it work the same kind of? I think
Uh,
didn't he do it last time too?
yeah, we spoke about it last time, but I kind of pulled it out of thin air and didn't explain it. And I want to try to convince you. So here's what I claimed anyway. So I claimed last time that if you take e and raise it to an imaginary number, I times x, then secretly this is somehow, it knows about trigonometry. It's the same as the cosine of x plus I times the sine of x, which seems very mysterious, right? How should e, this number, I'm just getting my pen set up, how should this number know about trigonometry? So I want to do some Python to show you why that actually is true. So first, for the Python aficionados out there, I'm going to import some libraries. So I need math. NumPy is a very common numerical library, and we're going to do plotting. So when you plot, you import matplotlib.pyplot, and I like to call it PLT. So I'm just giving it a nickname to call it later. And then this is a Jupyter notebook, so if you don't know, you click inside a cell, and I'm hitting the keys Shift and Enter at the same time. And then it runs. You see this little asterisk here? So the cell is running, and then when it's done running, the asterisk will go away. Okay, so now I want to understand this. This thing is called Euler's formula, this e to the ix thing. First, I want to make some side comment, because this is sometimes called the most beautiful equation in mathematics. If I take the number pi in radians and plug it into this equation, on the left side I have e to the I times pi. On the right side I have cosine of pi, so that's just the x coordinate. I'm going to draw it in a moment once the pen comes up. That's the x coordinate 180 degrees on the circle, plus I times the y coordinate, so that's just minus 1. So e to the I pi is apparently the same as minus 1. So if we add 1 to both sides of that equation, we find e to the I pi plus 1 equals 0. The first time I saw this, it gave me goosebumps. It's such a beautiful equation. It has 5 of the most important numbers in mathematics, e, I, pi, 1, and 0. And they just pop out in this beautiful way. Have you seen the Khan Academy video where he derives this?
I have not.
Okay, good. I mean, it's a classic. I think it's worth
To
seeing.
watch it.
Yeah, it's just so beautiful. But okay, why is this true? Right now, this is just magical. So first, what is e? Okay, so the people who have done pre-calc probably know what this number e means. It's in this numpy that I just imported, np. So you just call np.e and it tells you what e is, right? It's this number, it's about 2.718. It's just some number with some expansion. So where did that number come from? Sometimes when you learn about this in school, they tell you something about continuously compounded interest. But there's another nice way of defining e. You just add up a bunch of numbers, which you can see here. I'm zooming in a little bit. You add up 1 divided by the factorial of the integer 1, then 1 divided by 2 factorial, 1 divided by 3 factorial. What class do you guys
Um,
learn factorials in? Do you remember this?
we never learned it in any specific class. It was kind of like I learned it from Mr. Spurk, just because in calc last year we did something with like they were involved with something that we were doing, and everyone was like, "What's a factorial? Like, what are you talking about?" So he explained it, but there never really is a class that they say what it is.
I personally learned it in what's her name? I already forget. When she
Really?
gave me the statistics book, my
Morrow.
IP engine for yeah, Morrow.
Good. Melanie Morrow's a god.
Correct.
Okay, so that's a little disappointing. So people don't often learn about this. Okay, well I'll just tell you what it means to remind everyone. So the factorial of some number just means, oh, here's from when I was doing calc with other people. Okay, The factorial just means multiply all of the numbers up to that integer. So 3 factorial means multiply 3 times 2 times 1. So 3 factorial is 6. So I'll ask you guys, what is 4 factorial then?
1 times 2 times 3 times 4.
And what is that? If you can do arithmetic in your head better than me.
24.
Yeah, good. Do you ever play that card game in Gifted with the 24 game? Does anyone know what I'm talking about?
Yes, I do. That is the most unpleasant game I've ever played.
Okay, you're a heathen. I love that game.
Oof.
Okay, so let's just check that
I would
Python
not have
can do-
expected you to enjoy it.
So Python has a factorial, and indeed, factorial of 4 is 24. So it's very nice Python can do this. You can take factorials of bigger numbers if you want. As you can tell, they get large very quickly. So all I'm doing here is changing this number and then repeatedly hitting Shift-Enter to rerun, and Python is able to get the factorials. Okay, so now we're going to do our first serious Python loop. So what I'm going to do is try to convince you that this thing I wrote up here, actually I can use my pen now, this thing I said you can get the number e by adding up 1 divided by factorials. Each integer, 1 factorial, 2 factorial, 3 factorial. So I'm going to do that in Python now. What you do is start with e equals 0, and then I'm going to start adding all of them up. So I'm going to add each term in this sequence. So to do that, you use a for loop. So I say for n in range 0 to 100. So this means go through each of the integers, 0, 1, 2, up to 99. It stops at the one before the right endpoint. So I'm going through all of these integers, 1, 2, 3, 4, 5, blah, blah, blah. And then for each of those integers, I do the following. I take this number, which I defined up here, which started at 0, and then I add to it 1 divided by the factorial of the number n. So what Python is going to do when I hit Shift-Enter is it's going to go through and say, okay, 0, my e-approx is 0 plus 1 over 0 factorial, which is 1. And then it's going to say, okay, now I do it for the next one. So it adds 1 over 1 factorial. So now we're up to 2. Then it's going to add 1 over 2 factorial. So now we're up to 2.25. And it's going to keep going through. Keeps going through and adding them all up. So I'm going to run that now, and then I'm going to print out the result. Bam. Look at that. That looks very close. Let's just print np.e to see how close they are. Look at that. Down to like the 10th decimal. It's a very good approximation. Okay, so now hopefully I've convinced you that I can add up. Actually, this equation is wrong because I forgot to put 1 over 0 factorial. Because 0 factorial is also 1. Okay, anyway, so that's a way of getting e. Okay, so now you say, Christian, why are you telling me this? I thought we were trying to raise e to a complex number. You're just adding up 1 over factorials. Okay, well, as it turns out, e raised to some power x you can get by replacing all of the 1s in the numerator before up here with the number x that you're interested in. So if you want to raise e to the power x, all I have to do is put in x and then x squared and x cubed, and I keep adding in. I should really again have this x to the power 0, but that's simply 1, x to the 0 over 0 factorial, and keep adding. So this, I'll try to convince you, actually gives us e raised to some power x. So here's a question for you. This seems like a different formula from the one above, so what happens when I plug in x equals 1 in this formula? How is that consistent with our previous results?
Then that you'd be adding.
Yeah, so what are all of these numerators when x equals 1?
1.
Yeah, good, indeed. So all of them are 1 because 1 to any power is still 1. Right? So when x equals 1, this is 1, this is 1, this is 1, this is 1, and then it reduces to the sum that we saw before, which my pen's messed up, but it's this sum up here. And that's the same as e to the power 1. Right, good. So it seems like this thing is at least consistent with what we said before. So now I want to check and try to convince you that this actually works if we pick something other than 1. Right, so here's what we'll do. I do another loop. So it's going to be a for in range. So I define this function. We're doing a new ingredient here. When I say def and then put some junk, this is defining a function, and then that means later if I say this word and then put in some number, Python is going to say, oh, he defined a function. I'm going to look back at the definition of that function and run this code. So now every time I say those words later, Python's going to run this code. That's what happens. So what code do I run? Well, I just do this formula I wrote up here. So I take in the number x, and I do the same thing. I start with 0. I run through all the numbers from, say, 0 up to 100 to get a good approximation. And then this time, instead of adding 1 over n factorial, I do this thing, np.power x to the x comma n. So I'll ask you, the word is very suggestive, but what do you think this operation does? What is this? What do you think NumPy is going to compute if I say np.power x comma n?
E.
This thing? Well, that'll be the answer, hopefully, when we run this thing. But what is this expression? If I put in, or no, let's do a specific case. So what if I insert cell above? What if I do np.power 2 comma 3? If I run this cell, what do you think it's going to be?
I have no clue.
Let's see. Well, guesses from anyone else? Well,
I'm not watching what's happening. I'm just going to say 12.
12.
Nice.
Is it placing 2 to the power of 3?
Yeah, that's what the word power means. So 2 to the power 3,
Oh,
which I think
my
is
gosh.
good. Yeah. Good. So I think if power means what we think it means, this should give us 8. So let's see. Yeah, good. Okay. So what if I do np.power 3 2? What should I get?
One more. 9.
Yeah, good. Okay. So that's what power is doing. All right, so let's go back down here. So np.power xn, I think that's giving us x raised to the power n, right? So this is x to the n. And then that means this whole thing here, x to the n, I have a little fraction bar there. So this whole thing is x to the n over n factorial. Good. So that's exactly what we had in this sum up here, right? X to the number n, 1, 2, 3, whatever, divided by n factorial. So this function should give us this sum here, which I claim is e to the x. I still have to convince you of that. All I've done is written some function. We don't know it does what I say it does. We should actually check that I'm not, I don't know, sorry, I thought someone was messaging me. We should check that I'm not lying to you. So all right, let's do that. Here's what I'm going to do. I'm going to print out what we get by plugging in 5 into that function that I'm trying to sell you, right? I'm trying to sell you this used car over here or something, so you should check that it actually runs. So I'm going to print that out, and then I'm going to print out this second line. So what is the second line doing that I've highlighted?
Using e to the power of 5.
Yeah, this is e to the 5. Good. So if my function works, they should be the same, right? So let's see what happens. Bam. They're close. They differ in the 10th decimal place. Or sorry, the 10ths place. So they're reasonably close, but not great. So let me ask you a concept question anyone can answer. So if I wanted to change this function, so this is adding up 100 terms in this ... If I wanted to change this function to make it more accurate, so they agree not just to the tenths, but to the hundredths or thousands, what would I change in this function to make it more accurate? Well, let's see. So apparently the real answer is what we get by adding up all of these things up to infinity, right? So you would have to go up to, x to the 1,000 over 1,000 factorial plus x to the 1,001 over 1,001 factorial. So the real answer is a sum of infinitely many terms. But here I'm only adding up the first 100, and then I say, all right, that's good enough. And I'm just going to stop. So how could I make this better?
Just extend. Go. Wait, what? Oh.
Yeah, good, extend. So by that you mean add up more of the terms or something, right?
Yeah.
Okay, Robert has to go eat dinner or something. Yeah, so let's see what happens. If we extend it, let's keep 1,000 instead of 100. This should be better, right? Let's see what happens. Maybe not. Did I not run the code correctly?
We just changed like the slightest.
Changed a little bit, yeah. Shouldn't it, There we go. So now I'm going to keep 10,000 terms, and it's going to run for a little longer. But this time it should be better, I think. Or maybe it'll just take way too long to run. Interesting. Maybe 10,000 is too many terms. Yeah, that's probably too many. All right, I will kill it, but your answer is correct. It should be that if I could keep more of them, I would get a better answer. All right. Now the last thing for this part is the imaginary unit. So the punchline is that we're trying to argue that raising e to an imaginary power is somehow related to sines and cosines. But we don't know what it means to raise a number to an imaginary power, right? It's not at all clear to me what does e to the ix mean, right? I know how to raise a number to, I know what e squared means, right? That means take the number e and multiply it by itself. I know what the number e to the 1/2 means, right? That means take the square root of e. But what is e to the I? How can I multiply a number by itself an imaginary number of times? It seems not to make any sense. But if we say, okay, well, I don't really care what it means, I'm just going to go back to this formula. This formula seems to work pretty well, as we saw. It gives a reasonable answer. So what if we just take this formula and just plug in an imaginary number, right? So e to the I is apparently just put every x becomes an I to the 0 over 0 factorial plus I to the 1 over 1 factorial plus I squared is minus 1, right, over 2 factorial, and so forth. Let's just see what happens if we do that. It's just a guess, right? So I'm going to do that formula by plugging into our function. I'm going to raise e to the power of pi times I. Now I should say something. Python is very weird, so it uses the letter j instead of I. Right? So when I put 1j in Python, this really means I for some reason. I have no idea why. I should convince you that's actually what it's doing. So I'll do 1j times 1j. Oops, 1j. Run it. And what is it going to tell me? It's minus 1 plus 0j. So it's just minus 1. Kind of weird, but that's what they do. Okay, so let's raise e to the power of an imaginary number, pi times I, using our function. Bam. It's minus 1 up to a small rounding error. What's the rounding error? It's roughly 3 times 10 to the minus 16. That's very close to 0. That's a very small number. So the second part is basically nothing. It's almost exactly minus 1. So that's back to this nice formula. E to the pi I equals minus 1. Okay, good. For the...
Oh, and then it's all just like...
What'd you say?
It's all just one. Then it works. It would just work out then, right? Because the pi...
Yeah, it matches our formula, because the pi for cosine... Let's see, remember, what is pi? Pi is over here. Right, so here's pi. And then what are the x and y coordinates? Well, of course, the x coordinate's minus 1, and the y coordinate is 0. So minus 1 plus 0 times I is minus 1. So the formula works in that case, that one case. Let's see if we can do it in a few more cases and plot them. So this is how you plot in Python. All I'm going to do is take a bunch of x values. So these are going to be the things we plug into the exponential. What this a range does is all it does is take the numbers between 0 and 10 in steps of 0.1. Right, so it's just going to create a list of numbers that increase by 0.1. I'll just show you. It looks like this. 0, 0.1, 0.2, 0.3, blah, 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 up to 10. So it's just a bunch of x values in our domain, if you will.
Hey, Christian.
Yeah.
Allie has been typing for a while now.
I was looking at that too.
Oh, boy. I don't know if she's going to join. Oh, how nice. I'll respond to that after we're done. And then I'm recording, so she can see what we did if she wants. But okay, good. So what am I going to do? We saw that this thing gives us a bunch of numbers between 0 and 10. Here's another for loop, so I'm just going to run through all of those numbers. For each one, I'm going to plug that number times I into our function. So this is e to the I times that number. And I'm going to call that this output. And then I append, that just means I take this list and I put the output into that list. right? So this is just creating a list of x comma y values, right? The x values go from 0 to 10, and then the y values, the outputs, are just what we get by plugging each x into e to the ix. Right, I'm just trying to plot the graph, so I need a bunch of x and y values. Once I get those y values, which are all going to be complex numbers, all I do is take the real and imaginary parts to make it easier to visualize. And then this is how you plot. You do PLT, which remember way back here, I imported this guy and nicknamed him PLT to save typing. So I call PLT.plot, and then you do x comma y. So I'll plot the real parts and the imaginary parts of e to the ix. So I'll ask you to predict if I take e to the ix, which we think maybe should be cosine x plus I sine x, and then now I plot the real part. If I plot the real part of e to the ix, what is the shape of this graph? What should that look like?
Sine.
Yeah, it should look like cosine. So that looks like, what, like this or something, right? If I remember how trig works. So let's see if that's true. And bam! Look at that. Dead on. The real part is cosine, the imaginary part is sine.
Oh, wow, okay.
Perfect. So it seems to work. This is not a proof, but it's perhaps some evidence, some circumstantial evidence to convince you that this equation that I fed you last time with no justification is actually correct, because we can compute it and make the graph, and it seems to look like sine and cosine. Good.
You convinced me.
What'd you say? I convinced you?
Yes, you convinced me.
It's comforting. Good, good, good. Okay. Thoughts on any of this Python stuff before we talk about some of the equations similar to what Debbie's doing?
Yeah. Were you using your mouse the entire time, like when you were drawing?
Not my mouse. I'm using a little drawing pad, so Logan has one as well.
Okay.
This is my actual handwriting.
I was about to be impressed.
No, I can sign my name if you want. But
All right.
Good question though. Okay, next thing I want to show. This will be more relevant. The first stuff is really a Python warm-up in case you haven't seen much of it before. Let's talk about. Okay, so why are we doing this next thing? So the equation for everybody that Debbie is solving is something like a derivative, a time derivative, which tells you how fast is something changing, right? I shouldn't use a and b. That's bad. I should use, I don't know, x and y. I'll just use the same letters. I'll use the same letters I'm going to use in a moment. I'll call them r and j, as you'll see shortly what that means. So the left side is telling you how do these two numbers change in time, and on the right side are four numbers, a, b, c, and d, that tell you the change in terms of what you're doing right now. Right? So if you know what the numbers are right now, you know how they're changing in time. But we can approximate this. So this is an instantaneous rate of change. You can approximate this as, a finite rate of change, because we know, for instance, if you have, a line with slope m, y equals mx plus b, then the slope is defined as the change in y over the change in x. So if you want to know the change in y, I can say, okay, the change in y is just the slope times the change in x, right? It's not so bad. But that just means since the left side is the slope, this is just saying that we can write this as the change in r and the change in j, how much they change in one time step, is apparently supposed to be, let's see, it should be this thing. I'm going to do the matrix multiplication. So this will be AR plus BJ, right? Ignore the BJ. CR plus DJ, this thing, times delta x. What's delta x? Well, here our x is time, delta t. Right? So all this is saying is if you want to know how much r changes, just take a times how much r is now, plus b times how much j is now, multiply by how much time you're waiting, and that gives you how much r changes. Right? It's a nice, simple difference equation. No magic, no calculus, just multiplying numbers. And in particular, if we make our life easy and say that the delta t's are going to be 1, right? 1 time step, like 1 day or 1 minute, 1 second, whatever, then this simplifies a lot because this goes away, and we can just look at delta r. Okay, is that motivation okay for everybody?
Yes.
Good. So now let me tell a story about what those numbers mean. So we have 2 people.
Don't you dare ever say that again.
This is actually a story, though. So we have Romeo and Juliet. We have 2 people. Oops. We have 2 people, Romeo and Juliet. And the variable r of t is going to tell you how Romeo feels about Juliet at time t. So r of t could be a positive number, in which case he likes her. It could be a negative number, in which case he dislikes her. Whatever. This will later be the probability of being an electron or muon neutrino, but for now it's how Romeo feels. Similarly, there's another function j. So j tells you how Juliet feels about Romeo. Could be big and positive, which means she likes him. Could be big and negative, in which case she hates him. And then here I'm just copying that equation we had before. So remember, delta r, the change in r, that's r at the next time step minus r at the old time step. Right, that's what change means. You take the new one minus the old one. So I add r to both sides to find that r at time t plus 1 equals r at times t plus delta r. This is just the change. Right, so I'm just writing the change as new minus old and moving old to the right side, which is over here. Okay, so same equation as before. This gives us r at time t plus 1 in terms of r at times t and the a, b, c, and d. Okay, so you're probably asking, what are A, B, C, and D? What are the numbers? Well, you can pick different numbers, and they will mean different things. The story will unfold differently depending on what these numbers are. So I'll tell you 2 stories about 2 choices of A and B, and then I'll ask you about a third one. So suppose A is positive and B is positive. Let's just look at Romeo. So A is a positive number, and B is a positive number. That means that Romeo is eager. What do I mean eager? So if Romeo discovers that he likes Juliet, so that means r is positive at a time t, then I take positive times positive, and that means r at the next time t is bigger. Right? So if Romeo likes Juliet, at the next time step he likes her more. But similarly, B is positive. B multiplies how much Juliet likes him. So if Romeo discovers Juliet likes him, then positive times positive is positive, so he likes her more again. So that's what I mean by eager. If he likes her, then he likes her more. If she likes him, then he likes her more. Right? Kind of intuitive behavior. Let's pick a somewhat less intuitive behavior. What if A is positive, but B is negative? This is negative. So I call this narcissistic nerd for the following reason. If Romeo discovers he likes Juliet, R, then he likes her more. So he wants more of what he feels. If he likes her, then he begins to like her more. But if Juliet starts to like him, so this is positive, then I have negative times positive is negative. So the nerd, upon seeing affection from a girl, runs away. He retreats and likes her less. So that's narcissistic nerd. Alternatively, you could think of it as if Juliet hates him, then negative times negative is positive, and he starts to like her. So the nerd somehow likes cruelty, or I don't know. I don't know what to say.
Dominatrix.
Yeah, then maybe I should have said narcissistic sub. Okay. Now I regret the fact that I'm recording this for YouTube, but okay, I'll just move right along. I'll ask you, here's a new story. What if A is negative, so this is a negative number, but B is positive? How would you describe Romeo's personality?
The less that he likes her, well, wait. The less that he likes her, the more she likes him.
Well, we only know how much he likes her at the next time step, right? Because A and B only tell us about Romeo. Good. So if Romeo discovers he's getting a crush on Juliet, if R is positive, what happens the next day? So if R is positive at time t, and we have a negative times positive, what happens at the next time?
It's still negative.
Yes, this is negative, so that means at the next time step, it's smaller than it was. So if Romeo develops a crush on Juliet, then he begins liking her less. He retreats. He's I would describe this as cautious, right? He's he doesn't trust his own feelings, right? If he gets a crush on her, then he retreats and likes her less. But what happens if she starts to like him? What if Juliet expresses interest in him? So J is positive.
He will not be cautious.
Yeah, good. So if she expresses interest in him, then R increases. So this is an interesting balance, because if this cautious personality, if the girl likes him, then he'll start liking her. But if he starts liking her in the absence of interest, then he kind of retreats and doesn't do anything about it. So that's why I call it cautious. Kind of an interesting story. Someone's pinging me, which is probably to laugh at something I just said. It shall decline. It shall decline. Interesting. Yes. Right, indeed. So it'll go back to 0, basically. Okay, good. Enough stories. Let's actually do some Python. So I've written a big block of code, and I just want to explain what all the pieces does. This is what's called a simulation. So it's the same type of code you'll run, or Ali will run on the neutrinos. So what does this do? It's a function, because I have a def. So that means Python will run this code whenever I say simulate. What do I have to hand the function? I hand the function R_initial, which is how much Romeo likes Juliet at the beginning, J_initial, which is how much Juliet likes Romeo at the beginning, and then those 4 numbers A, B, C, and D. And then I could tell it how many time steps to run for, but this thing means it'll default to 10 if I don't tell it anything. Okay, so then what do? You hand me those numbers. All this code does is it defines some variables. So it takes current Romeo, which starts at the initial, current Juliet, which starts at the initial, and then it's going to make a list of outputs. That's what these brackets mean. These are just starting a list with now 1 element, but we can append other elements later. So I make a list of the Romeos and a list of the Juliets at each time, and then I just go through each time step and update them. So that's another for loop. So for n in range of the number of steps, this is going to run through all the numbers from 0, 1, 2 up to here 9, because it skips the last one. For each of those time steps, what do? Well, I just use the equation. Right? This is the equation we saw before, that the change in Romeo, delta R, is supposed to be A times the current R plus B times the current J. Similarly, the change in Juliet is C times the current R plus D times the current J. It's the same equation from before, just in Python. Then once I have the changes, I have to update the current Romeo and Juliet. So this is the updating step. Updating just means I take the current Romeo, I add the change, and then I assign that to be the new current Romeo. So this equation looks weird. It looks like I'm saying thing equals thing plus other thing. But you should really read this equal sign as assignment, right? So I'm taking the old current Romeo and reassigning him to the new value of current Romeo plus the change. So this is the update step. And then what do? Well, I'm trying to make a list of all these guys, so I better append them to the list. So I add to the list. And then at the end I get all the Romeos and all the Juliets. So I'm going to run this and show you what the plots look like, but first I'll ask you to think about what's going to happen in one particular case. So here's the story we're going to investigate. Suppose we start out at the initial time and Romeo likes Juliet. So R equals 1, it's positive. Juliet has not noticed Romeo. She doesn't know shit about him, so J equals 0. Neither likes nor dislikes. And what about the A, B, C, and D? Suppose they're both eager. That means they're all positive. So eager means if either person likes the other, they begin to like them more, and if either person notices the other is liking them, then they also start to like them more. So if we start with R positive and J 0, and they're both eager, I'll ask you to describe what happens in the long run. What's the outcome of this relationship?
Infinity.
What do you say?
I said infinite likeness. They
Infinite
like each
love.
other.
Yeah, basically. Yeah. How does that happen? So take me through step by step how we get to infinite love.
Well, Romeo starts liking Juliet. Juliet sees that Romeo starts liking her, so she starts liking him. And then vice versa, Romeo sees that Juliet likes him, and so he likes her more, and then Juliet will like him more, and so on and so forth.
Good. Yeah, we get a feedback loop where they're both feeding off of each other's love and their own love as well. So
Parasites.
yes, good. Let's see if that actually happens. So I'll run the simulation, start with Romeo at 1, Juliet at 0, and all these guys are positive. I'll put them at 0.1. And then I use plot again. So I'll go. Oh, simulate is not defined because I forgot to run this code. I explained it and didn't run it. There we go. Now let's do this. Yeah, good. So at time 0, let's just interpret the plot. At time 0, the orange curve is Juliet, so Juliet doesn't like him at all at time 0, but Romeo likes her. And then later, Juliet starts to like him, so J is positive because she noticed that Romeo likes her. And then Romeo similarly is noticing both his own feelings and hers, so R grows, it gets bigger. Then you can see it just starts to skyrocket. I cut it off at 10 because it gets so high.
That's the end of their life, 10.
They have 10 days left, and then they're both dead. Well, that's what happens in the actual Romeo and Juliet, so...
When he's not, like, it's not far off.
Let's do 100 steps and see how fast... See what happens? It gets so big, you can't even see the Romeo, just because it gets big so fast, but... yeah, so...
That's what she said.
Ouch. Alright, so that's infinite love. I'll ask you maybe 2 more. So, here's a nice one. Suppose Romeo and Juliet are out of touch with their own feelings. By that I mean A equals D equals 0. What does that mean? So, that means the change in Romeo's feelings has nothing to do with Romeo's feelings at time t. It doesn't affect anything. He only cares about how Juliet feels. And similarly, J, well, has D equals 0, so her feelings only respond to R, how Romeo feels. So that's out of touch. If that's true, then we start with, let's see, oh, I didn't tell you about the signs of the other ones, but, oh no, I did, I told you over here. Okay, so they're out of touch. Juliet starts liking Romeo, so J equals 1 at the beginning. And then here's the personalities. Romeo's a narcissistic nerd. Right, that's the one where he responds to his
Her.
Yeah, her feelings with a negative, right? So there's a negative sign. So he retreats if she likes him. Juliet is eager, so she increases her feelings if Romeo likes her. So Romeo retreats from love, and Juliet seeks love from the other. Okay, so then what happens in this case? It's a bit trickier.
They will go infinitely in opposite directions. They will, I guess, start to hate each other.
Yeah, but we have to be careful because indeed they're going to go in the opposite directions first because Juliet is going to be up here, J equals 1, and Romeo's going to be down here. Now, Romeo's going to run away because he sees Juliet likes him. So when he runs away, Juliet doesn't care about her own feelings. She just cares about Romeo's. So she says, oh, he doesn't like me. And she's eager. Eager people stop liking when the other person doesn't. So she's going to go down and start getting negative. What happens when she goes negative?
Oh, he goes up. Okay.
Yeah, he changes his mind. He's like, oh, man, she's ignoring me. I want more of that. And
What?
we get this very strange back and forth, right? Because... remember, nerd means you like the person more if they dislike you, and you like them less if they do like you. So she starts liking him, he runs away, then she doesn't like him, and he's like, now I want it, and then it oscillates. So we get this strange behavior, and I want to make the plot now, where...
Romeo and Juliet finally makes sense.
Yes. This is maybe not a perfect model for human relationships, but you may have had some experience which... is similar to this. So anyway, yeah, this is precisely what happens. So good. Juliet starts liking, then gets discouraged, and then he starts liking her, and she's like, well, maybe I have a chance, and then she becomes interested, and then once she's interested, he doesn't like her anymore, so there's this, I like to, you might say, playing hard to get, perhaps?
Wait, is Romeo a tsundere?
Tsundere? What is that?
Never mind.
Okay.
What is life?
Sorry. You may have noticed that these are exactly the plots of cosine t and minus sine of t. So before you criticize me for telling love stories or lack of love stories, I should remind you that this will be mathematically identical to the neutrinos eventually. So good. But it's still fun for now, so I'll do one more, and then maybe we could take a break. So, one more. Say Romeo is eager, so he responds positively to both his own feelings and hers. But Juliet has a personality which I describe as hermit. What is hermit? Hermit means that both C and D are negative. So Juliet retreats. She likes Romeo less, both if she likes him and if he likes her. So Juliet runs away from positive feelings. But of course, if these are negative, then it's reversed, and she'll come back and start liking him. So Juliet just does the opposite of what she wants and what Romeo wants, which is very counterintuitive. But okay, so if Juliet just does the opposite of what she wants and what Romeo wants, and Romeo is eager, and we start with mutual attraction, so they're both positive. J equals, say, 1, and I don't know, R equals 2 or something. Actually, I think I made it the other way, 2 and 1. What happens in this scenario?
First, they both start to go down, but then as they go down, Juliet starts to go up, and then Romeo starts to go up.
Yeah, we're going to get some, because I agree at the beginning. Let's see. At the beginning, Juliet's definitely going to go down, because she retreats from her own feelings and Romeo's. So if Juliet's at 2, she's going to start going down. And then Romeo, I think, is going to start originally going up, because he's originally saying, oh, I like her, she likes me, this is great, everything's wonderful. And then it gets negative, and then something mysterious happens. He's like, what happened? I thought everything was wonderful. Then we have some... it's not clear at this point what's going to happen next, because he still has his own feelings. He responds positively to his own feelings, but he's also unhappy because it seems that Juliet doesn't like him anymore. So is he going to go back down, or is he going to reach some, I don't know, balance? It depends on the numbers, so let's run it and see what happens. Oh, interesting. So we get a deadlock. So Romeo goes up to positive infinity. So Romeo goes to positive infinity. He develops infinite love. And
Oh, this is only 10 days.
Well, do you want me to extend it more? Let's see what happens when they're 80 years old. Let's do 100 times.
If he's eager and she is a hermit, as she goes down, wouldn't his eagerness start to put him down as well?
It will, and this is why not only the sign, but the magnitude of these numbers matters, right? Because I was sneaky, and I choose...
If his feelings are high enough, he will just ignore his eagerness, I guess.
Yeah, exactly. So if his feelings are huge, this eagerness is going to compensate for the desire to kind of run away when he sees that Juliet doesn't like her. But here I've chosen them to be the same magnitude, right? So these things, as it turns out, if he likes her, the positive contribution from this outweighs the negative contribution from this, and he goes up to positive infinity. So he goes to infinite love, and she goes to infinite hatred. So he's just pining after her, and she despises him. But indeed, let's see what happens if we change these numbers. So what if he cares more about her feelings than his own feelings? So we make this 0.1. Then I think we'll get a different result. Ooh, now we have some interesting oscillations. Notice the magnitude of these oscillations is different. He oscillates more. What if I make this 0, so he only cares about her feelings? What happens now? Ooh, now they both tend to apathy. So he starts liking her a lot, then hates her, then likes her a little bit, then hates her a little bit, but as we go to infinity, they both...
Hey, marriage.
Oh, hey, it's marriage. Yep. All marriage is an oscillating love and hatred, and ultimately ending in apathy. Oh, good. Marriage. Well, that was the best possible way that I could have concluded this demonstration. But okay, good. So hopefully, well, if Allie goes through this, it'll help her with writing the simulations, because then the only thing we'll have to do next is, we can use the same code actually. We just need to change these A, B, C, and D to complex numbers, right? Have an imaginary piece, and then get the probabilities for neutrinos out of this instead of plotting love and hatred. But I like to tell this story because it's a fun way to introduce it. Okay, thoughts on the Romeo-Juliet stuff?
No thoughts.
No.
I
Thoughts?
agree with Logan. It is like marriage.
Yes, eventual apathy.
Even though